So we're going to look at separable differential equations. So, real quick definition of separable differential equations. First order differential equation is just something like this, right? We have a first derivative is equal to some function of x and y, okay? That differential equation is separable if it can be written in this form. If it can be written as dy dx equals some rational function where we get a function of x in the numerator and y in the denominator, and you can probably see why. Then that allows us to, when we cross multiply, so we write this in differential form, right? We write the derivatives. What we end up with is a differential form of a derivative on the left and a differential form of a derivative on the right, where we've got only some function of y times dy on the left and a function of x times dx on the right. And then we're able to just integrate to solve the differential equation. We don't have the variables mixed, and so it's easy to integrate, right? All of the, assuming these are integrals that we can do, that they match and we're able to manipulate the integrand and do the integrals, this is just the kind of stuff we've been doing now for quite a while, okay? It gets much more difficult if it's not a separable differential equation and you get integrals involving x's and y's. Well, that's when you need multivariable calculus, right? That's when you have to be able to take partial derivatives, derivatives of some function of x and y with respect to a single variable, and that's higher level stuff. That's for later. Okay, so some examples like this is separable, isn't it? Right? I can push the y's to one side and the x's to the other side, and look what I end up with. I get on the left side dy over secant y, which would just be the same thing as what? Dy times cosine y dy. And on the right side I've got x dx, and I can solve that one by integrating both sides. Here's an example of one we could not solve, right? We're stuck here because I've got this function sine of both x and y, and so I can't separate the variables, right? At least not without doing some trickery. I've got to do a bunch of, maybe I could appeal to some trig identities or something like that maybe, but that it would be tough to do, okay? All right, so let's do an example here. This one is pretty straightforward. I want to spend more time looking at the growth and decay stuff today. That's really interesting. So what about something like this? If I've got dy dx equals 3xy squared, well, I can separate the variables here. So they want us to find a general solution and then find a particular solution if we know that when x is 1, y is 2. Okay? So what would we do? Okay, so first thing we would do is we would multiply both sides by dx, and I would divide by y squared. So I push the y's to the left side, the x's to the right side. And now look, now I can just integrate both sides, and these are two pretty easy integrals, right? Here I've just got the integral of y to the negative 2 dy, and then 3x dx, and those are a piece of cake. You guys can do those, right? So the integral of y to the negative 2 dy would be what? Negative 2y to the negative 1. Is that right? No, sorry, negative 1y to the negative 1. So we just get negative 1 over y equals, and then over here we're going to get 3x squared over 2. And then we just lump all the constants in and put them on one side. Just lump all the constants on one side, and there's our general solution. Is that the best way to write it? Well, it's a way to write it. I mean, I guess we could solve for y or something if we wanted to, but that's fine. I mean, there's a solution that involves x's and y's, right? And you could rewrite it if you want to. But we probably don't want to initially anyway because we haven't solved for c yet, right? So when we take the boundary value or initial conditions, whatever you want to call them, particular conditions, and plug those in, look what happens. If we evaluate this when x is 1 and y is 2, then we can solve for c. And it turns out, I guess, if we do all this math, we're going to get c equals negative 2. And you guys can do this. Is in your online textbook. You can just look at this one later if you want to look at it in more detail, but I don't think you need to. So now if we know c is negative 2, we just plug that back into our general solution, and we get the particular solution. There it is. Okay, and if you wanted to rewrite that, you certainly could. We could clear the fractions by multiplying both sides, or multiplying everything through by 2y, and you know, we could write it in a different form if we wanted to. Okay, give me thumbs. How we doing on that? That make sense? Okay. All right. So more interesting are our growth and decay models. So we could talk about two kinds of growth and decay. We could talk about uninhibited growth and decay or inhibited growth and decay. Uninhibited growth and decay means that the growth or the decay just continues forever. Okay, there's nothing stopping it. And this is really simple. This is a really simple model to consider because typically what's going to happen in nature, you know, if we look at applications in biology and physics, for example, what you see is that the rate of change of some quantity is proportional to the amount of that quantity. Like if you look at the population growth of you know, some, I don't know, lemmings or something, right? At least initially, after a while, of course, they're going to run out of food and room, and then things change. But at least initially, it's going to follow this kind of a model, where the rate of change of the population of lemmings is proportional to the number of lemmings available, right? Because the lemmings have to reproduce. You see it with bacteria, right? The number of the more bacteria you have, the faster the rate of change of the bacteria is going to be, right? So this is the simple model that dictates or that underlies uninhibited growth and decay, right? And always just the rate of change of the substance is proportional to the amount of the substance. And here K is just the constant of proportionality. If it's a growth model, K is positive, right? So if you're talking about like a population growth, K is going to be some positive value. But if it's decay, like you could be looking at radioactive decay, for example, where the amount of the radioactive substance is as it decays, you lose, you know, the amount gets less and less. And of course, the rate of decay is going to be proportional to the amount of substance there is there to decay, right? And so for decay, the constant of proportionality, for decay, the value of K would be negative, right? If the population is decreasing. Doesn't that make sense? Because the sign of K determines the sign of the derivative, right? Positive derivative means growth, and negative derivative means it's the amount of the substance is decreasing, so that would be what we'd call decay. All right, so we can solve this, and let's just go through that real quick. How we would solve this. If this is our, get that out of the way for a second. This is our starting place, right? If we've got growth or decay. Right, that's the differential equation. And do you guys see where we get that differential equation? Because that's something you're going to do more in the future. Is a lot of times you'll write a differential equation to match the conditions that you're interested in studying, right? Because usually in physics and in biology and you know any place where we might want to look at a dynamic system, we're able to look at, you know, the rate of change of the substance is something that it's easy for us to model, right? And in this case, again, if it's uninhibited growth or decay, all you have to remember is that the rate of change is proportional to the amount of the substance. So that's really where we're starting right there. Okay, that's the differential equation we always start with. So we separate the variables. We're going to push the A's to the left and the T's to the right. And then we just integrate both sides. Okay, so what happens when we integrate here? What do we get on the left? What's the integral of dA over A? Natural log. And we don't need absolute values because A is, you can't have a negative amount of some substance, right? So we just get natural log of A plus some constant is equal to, how about the right side? K is the constant. on the right side, the variable of integration here is t. kt, right? Plus c. Okay. So there it is. That's the solution, but it's just not in a very convenient form, right? So we want to solve this thing for a, right? A is, we're looking for a of t. Okay, but what must that value of c represent there? Or what could it represent? What would be a convenient constant that we could pick for c, do you suppose? Given that this is some real dynamic system. K is the constant of proportionality, but how could we ascribe a value to c here? Is there a convenient, let me pose the question this way. Is there a convenient value of t we could plug in and evaluate this expression at? I mean, like zero, right? Does that make sense? Like at t equals 0, then the value of a would just be, because a is a variable, right? A is our output variable here. It's the dependent variable. The value of a when t equals 0 is just the initial amount, right? Everybody see that? So let's make a note of that here. So at t equals 0, a equals a naught, which just stands for the initial amount, right? Okay, and so if we plug that in, look what happens. If we plug in 0, we just get the natural log of a naught is equal to 0 plus c. So that's the value of c. C is equal to the natural log of a naught. Okay, and so we can plug that back into our equation, and this is what we get. The natural log of a equals the natural log of a naught plus kt, right? Now, a lot of times people will combine those logs, which you can. It's fine to do. Like I think in our book, if you look at the way that they derive the outcome for this, when they solve for a, the way they go about it, they combine. They say log of a minus log of a naught, and then I can write that as a log of a ratio of a divided by a naught, and that's fine to do. I never do it that way. You just as easily could. I always do it this way. I always just say, now if I want to undo logs, I'm going to exponentiate both sides, right? So we get e to the log a equals e, e to the left side equals e to the right side, equals e to the log a naught plus kt, right? Okay, well, what do our exponent rules say about this? If I have something like a to the m plus n, isn't that equivalent to a to the m times a to the n, right? So we could just write this as e to the log a equals e to the log a naught times e to the kt, and exponential functions and natural logs cancel each other, right? So look what happens here. Those guys cancel and those guys cancel, and we end up with the answer a, we'll write it as a of t, how about, equals, that's just going to give me an a naught e to the kt. So there's the solution of our of our separable differential equation, right? We end up with a model that always looks like this. So this is our uninhibited growth and decay model right there, where k, again, is just the constant of proportionality, and the other constant now makes sense. A naught is the initial amount, okay? Give me thumbs. How's that? Is that good? So you can always just jump right from here down to there without necessarily showing that work. A lot of times I don't know. I mean, like if I haven't done this in a while, I just crank through that. It takes 2 seconds just to solve the differential equation, and then you know you got it. Okay, that's what we end up with. All right, so let's use this. So I guess real quick, what do the graphs look like? So if we solve this differential equation, if k is positive, I mean, not surprising, you get an exponential growth model, right? If k is negative, you get an exponential decay model. It's no big deal. Okay, that's what the graphs look like. And you can see with the growth model, it's uninhibited growth, which means that it's, in theory, this thing would just grow and grow and grow forever. Now, the universe doesn't really support that very often, so at some point, that's probably not going to happen, but it may be way down the line. So for much of the parts we're interested in, the model might look exactly like that. Uninhibited decay, it's just going to asymptotically approach zero. Okay? So, examples. Okay, what about this one? We'll look at this. We have a colony of bacteria that grows at a rate proportional to the number of bacteria present. So that's present. That's really important. That's telling us, oops, that's telling us that this fits our differential equation, right? That's telling us, like, if we're going to say that n is the number of bacteria, that's giving us this differential equation, isn't it? The rate of change of n is proportional to the value of n, okay? Okay, so then what do we know here? If the population of the colony doubles in 5 hours, how long does it take for the population of the colony to triple? Okay, so let's just go ahead and jump right down. We already solved the differential equation. So let's just jump down to what we know the solution is going to look like. What's that going to be? N of t equals what? N naught. E to the kt, good. Okay, we know N naught stands for initial, the initial value or the initial population size, which we actually don't know up here. But we don't need to know it either, do we? Because the way this question is phrased, we don't ever need to know what the initial population size is because we just want to know when whatever that size is, we end up with or 2 times that size, right? When you see stuff like this, when you're given problems, growth and decay problems, where you're given language where it says things like doubles or triples, what you're inevitably going to see, and I kind of want you to watch this play out, that just means that the n naughts are not irrelevant to the answer, and so they should algebraically cancel out when we're doing the math, right? And the math gods are smart. They'll ensure that that happens, I promise. But the other constant we do need to know. We need to know the growth constant k, and so we need some boundary value or initial value or something, whatever you want to call it, particular value, to solve for that, and they give that to us. Here it is, right here. The population of the colony doubles in 5 hours. Okay, that's telling us it's telling us exactly what the outcome is going to be in a specific amount of time, and so that constitutes an ordered pair, right? That's a point. That's going to allow us to define the trajectory of this family of curves that we're looking at, right? Okay, so if we plug in that information, the population doubles in 5 hours, then how am I going to turn that into, how do I interpret that? How do I write an equation to match that statement? So what's the value of t that I'm going to input? 5. What's the value of n that I'm going to input? Say it again. Yeah, so I want to know what's the variable. N naught is a constant. What's the value of n we're going to plug in if the colony doubles in 5 hours? 2 n naught, right? Everybody get that? See what I'm saying? So then we're going to we end up with this equation. 2n naught equals n naught e to the kt. And what do you know? Sure enough, you love this. When this happens in math, you cancel a constant. That's great. You don't have to even worry about it. Okay? So if we solve this thing, then we just get 2 equals e to the kt. My goal here, oh, and we know what t is, right? We know we're plugging in 5 for t. So this becomes 2 equals e to the 5k. How do I solve for k? Say it again. Natural log, yeah. Natural log both sides. Natural log of 2 equals 5k. So k just equals natural log 2 over 5. Okay? And as you do a bunch of these kinds of problems, what you see, a lot of times you talk about doubling time, right? Like when you're talking about financial stuff, you want to talk about the doubling time of your principal that you're investing, or you talk about the doubling time of a population, something like that. You always end up with the same thing. The doubling time is always just going to equal, the constant is given by log 2 divided by the doubling time. Okay, does that make sense? Okay. All right, so now we can plug that stuff back into our model over here, feed that back into the model, and we have a specific growth model. N of t equals n naught e to the, and we just said k was log 2 over 5. So we get e to the log 2 over 5 times t. There's our specific growth model for this colony of bacteria. Okay? Now all we have to do is just plug and chug, right? We want to know how long does it take for the population of the colony to triple. So what would I do? Yeah, right? We're evaluating this. We're trying, in other words, what we're trying to do is find t when n of t equals 3n naught. That constitutes tripling, right? So we get 3n naught equals n naught e to the log 2 over 5t. Look, the n naughts cancel. Log both sides. Log 3 equals, then that's going to cancel the e, and I just get log 2 over 5t. So if I want to solve for t, I'm just going to multiply each side by 5 over log 2. What's that going to give me? 5 times log 3 over log 2. And log 3 over log 2 is I don't know what that is exactly. It's going to be, can't remember what they put, 7 or 8 or something like that. Yeah. So it works out to be, if you do it as a decimal, it's going to be, evidently it's roughly 8 hours. Okay, make sense? That's pretty cool stuff, isn't it? I mean, it's that you can come up with a differential equation and solve for it that easily. That's just, this stuff always really, I really like this stuff. Okay, so rate of decay, like we mentioned, this is the same model, only k is negative. Now there's a really interesting application of this, and I'm sure you've all heard of this before, but I want to kind of explain this a little bit, because this is something that is really just generally misunderstood by people, and probably not you guys, but people in general just have a hard time with radioactive dating. People question the validity of radioactive dating, and you never should, because it's super accurate. Okay, so here's how it works. The half-life of a radioactive substance is the time required for half of the substance to decay. Now, if you look quantum mechanically, there's a certain probability that any one particular particle is going to decay. It's driven by the Schrodinger equation, and there's a large degree of uncertainty there. But the probability is exactly understood. And so when you talk about a huge number of particles, and even a small sample, radioactive sample, is containing millions, if not billions, of most likely it's going to be billions or even trillions of particles, right? And so the half-life is exactly accurate. I mean, it doesn't waver at all. It's the same concept of, like if you flip a coin 1 billion times, what percentage are going to be heads? I mean, it's going to be 50%, to within a fraction of a percent. Now, sure, you might end up with 40 more heads and tails, but out of 1 billion flips, that's nothing, right? It's 50%, okay? Same kind of thing happens here with half-life. You guys just get this, it's exactly the same every time for any macroscopic sample size. Okay, so you can use this. Carbon dating, it's a method we can use to determine the age of some kind of organic artifact, right? Uses the fact that all living organisms contain 2 kinds of carbon. There's 2 kinds of carbon in the environment. There's carbon-12, which is stable, and carbon-14, which is radioactive and decays. So when an organism dies, the amount of carbon-12 present, of course, remains unchanged because that's stable, but the carbon-14 decays, right? And so by just measuring the amount, the relative percentage of carbon-14 in an artifact, you can determine very accurately how old it is based on how much of the carbon-14 has decayed. Okay, do you have any questions about that? Because my original question when I heard about this was, well, why would, how would you ensure that the amount of carbon-14 is always the same when the animal dies, or when, this was used, doesn't have to be an animal, it could, you guys remember, there were some sandals, woven sandals that were found at Fort Rock in southeastern Oregon, and it pushed back the date, they were 14,000 years old or something. It was just crazy. I mean, we didn't think there had been indigenous people in the area at that time, but man, it really pushed back the date that we could identify there definitely were people there. So how do you know that when the plants are harvested to make the sandals or the animal dies, that the amount of carbon-14 is always the same, right? Well, here's why. Because carbon-14 is constantly being produced. It's emitted by volcanoes, for one thing, but even more accurately and more, it's more reliably constant source of carbon-14 is just in the upper atmosphere. When neutrons, alpha particles when the neutrons that are embedded in the alpha particles from solar wind or cosmic rays, when they encounter the gases in the upper atmosphere, they just produce carbon-14 at a very constant rate, and it's very quickly absorbed into carbon dioxide. And so there's this constant influx of carbon-14. You've got the same amount that a dinosaur had. It just doesn't vary. Okay, so it's easy. You can see how that works. There are other radiometric substances that you can also use depending on how, yep, question? Is it the same amount relative to the volume of animal? Yeah, it's just so when you eat a hamburger, you're eating, it's carbon, you're eating a lot of carbon, and so there's a fixed amount of that carbon is carbon-14. And so it's just going to be, so if you're a dinosaur and you're eating a really big hamburger in the form of a stegosaurus or something, then you're just getting more carbon in there, but the percentage of carbon-14 is the same regardless. See what I'm saying? You don't have to. All you have to know is if you take a sample of carbon, you're going to see what percentage of that carbon is carbon-14. You don't have to ever know how much there was initially. You just have to know. Does that make sense? In other words, every living thing has the same ratio of carbon-14 to carbon-12 when it's alive, because you're constantly replacing the carbon atoms in your body. You get that, right? That it's kind of an interesting concept. I mean, you are you, right? But you're not the same you on a molecular level that you were when you were younger. I mean, you're constantly exchanging the materials that make up you. You're more of a, what would be a good way to describe you? I mean, because it's not really the constituent material components that build you. You're kind of an emergent pattern that comes, and it's really the information that makes you is stored in the organization of the particles that come and go. It's not the particles themselves. Kind of interesting. Yep.
There's a Greek myth about a ship. I don't know what
Yeah, that's, yeah.
Replace every plank one at a time.
Yeah.
It's still the same ship.
Yeah, that's a good way to think about it. Yeah, that's right. If you and that comes up a lot when you talk about this stuff. You know, if you're constantly replacing one plank every year on this ship, I don't know if it was every year, but at some point every plank has been replaced, but we still recognize the same ship, right? And that's a good analogy. Yeah. So you can see though that if you want to go back, the half-life for carbon-14 is 5730, I believe. It's not very long. Does it say that in there somewhere? Maybe it's in the next example. I'm pretty sure it says it on this chart, I bet. Yeah, 5730. So, you know, if you're trying to date something that's millions of years old, carbon-14 is not the way to do it because you start to get such vanishingly small amounts of carbon-14 that the measurements, you introduce some uncertainty in the measurements and it's not very accurate. So typically we do like radioactive, you'd use something like argon dating or potassium dating or something like that where it's a much longer half-life. If you look at the half-life of potassium, it's 1.25 billion years, right? So you could easily, like if you wanted to look at something like dinosaurs, well, I mean, that's almost even too long in a way, right? I mean, dinosaurs, you're looking back hundreds of millions of years, or was it 70 million years would have been the most recent. That's when I think they were extinguished. But if you're going back, you know, 100 million years or 150 million years, you know, that's only 10% of that, right? And so that's workable, but you might want to pick, that's why like argon dating might be better. If you're looking at non-living things, like if you want to look at, for example, trying to date the planet, looking at early rock formations, then you want to look at things like, you know, like potassium or uranium-238. Look at the half-life of uranium-238, 4.5 billion, right? Which is roughly the age of the Earth, right? So that fits well if you're trying to establish a date of, you know, formation of the Earth. Yeah. In an organism?
How do they measure the amount of uranium left? The amount of carbon-14 left?
Or like carbon-14, okay, so all you'd have to do is if you find, it has to be something that's organic, and it has to be something that would have maintained an equilibrium with the atmosphere. So like an animal, that's easy because we respirate, right? So you're constantly breathing in carbon dioxide, which is a part of the gas, you know, part of the air you breathe in, and so you're constantly exchanging that carbon through eating things and through the atmosphere. All you have to get is just some viable piece of organic material, which is hard to find. The further back you go, the harder that is to find. It's pretty tough to do. Like with dinosaurs, it would have to be probably a piece of the bone. It would have to be something it'd be pretty hard to find. I mean, there are some rare cases where they've actually found tissue, but that's really rare. Now, if you go back to like Ice Age animals, which is what carbon-14 would be used for typically, that's easy. Just some mammoth gets frozen in the ice. You go, there's a whole, that's all carbon, right? So you take any piece of the carbon you want, really. I don't know what the best, honestly, I've never done this before, but probably the scientists would know. We want to use a piece of the tongue or something, I don't know. It's for whatever reasons, but you could theoretically even use like hair would work. Okay. So let's do a problem. So let's say we find the skull of an animal in an archaeological dig, and when we measure the amount of carbon, and you do that through like mass spectroscopy, or you could use like a liquid scintillation technique, or I mean you could compare. I mean there's a bunch of different ways you could do it, but probably most often it would just be you'd probably be doing, well, I don't know. I mean, you could do any of those. You know, I would assume mass spectroscopy is probably what you would do. But we measure it using some technique, and we find it contains 20% of the original amount of carbon-14. So if we compare that to a modern skull, it's only got 20% of the amount of carbon-14 that a modern skull has. We know the half-life is 5730 years. How long ago did the animal die? Okay. So what are we going to do? Well, we know we're starting off with our trusty model. So if we're going to say y is the amount of material, we know dy dt is proportional to y, right? K is going to be negative here because it's decay. We know that the solution to that, we could do the math, but we're going to get the same result every time. Y of t equals y naught e to the kt, right? Okay, so y naught is the original amount, which we don't know, but we don't need to know because we're talking about percentages. So those are going to cancel anyway, but we do need k. Okay, so how am I going to find k? Say it again. Point. Oh. Okay, that now eventually you mean 0.2, I think, right? Contains. Eventually we're going to do that, but first we've got to find that's the value we're going to use to actually solve for t, right? But before we can do that, we need some other condition here that's given to us to solve for k. What do we know specifically here that's going to allow us to solve for the value of the decay constant? Now think about the value of the decay constant is going to be a property of the material, right? Do I know some information about the material here that would be useful? Half-life. Yeah, exactly, right? I know the half-life. The half-life of carbon-14 is 5730, right? So that tells me that, in other words, I'm going to end up with half of my initial amount when t is 5730. Everybody agree? And look what I can do. I can cancel the y naughts, okay? It's irrelevant, or it's independent of the initial sample size. We just know that however much we had, half of it is left after 5730 years. So if I log both sides, I get the natural log of 1/2 is equal to 5730k. And the natural log of 1/2 is the same thing as the natural log of 1 minus the natural log of 2, right? What's the natural log of 1? 0, yeah. So we get negative log 2 equals 5730k. So k must equal negative log 2 over 5730. Okay, and you could, what if we weren't using carbon? Well, I just would have had a different number here for the half-life. This is the result you're always going to get. K is always equal to, thank you. K is always equal to negative log 2 divided by the half-life of the material you're talking about, right? Okay, so if we plug that back in then to our model, we're going to get y of t equals y naught e to the negative log 2 over 5730 t. And now we'll use this other piece of information. 20% of the original amount remains, right, when we analyze the sample. And so here's where we would do 0.2 y naught equals y naught e to the negative log 2 over 5730t. Cancel the y naughts. Okay, we knew that had to happen. Log both sides. And if I log both sides, I get natural log of 0.2 equals negative log 2 over 5730 times t, right? Solve for t. And what am I going to get here? 5730 times negative log 0.2 divided by log of 2. And that negative sign's that bugging you? Well, what's going to be the log of a number greater than 0, the sign of a log of a number greater than 0 but less than 1? Think about a log function. Right? It does that. It's negative valued in the domain where t in this case is greater than 0 and less than 1. So it's all going to work out. T is going to be positive. And if we do this, what do we get? I don't know. 0.2 over 2, that's going to be like 1/10. Oh, I don't know what that's going to be. Years or something like that, I bet. So we had negative 5730 natural log 0.2 divided by natural log 2. There it is. Oops. So that skull was 13,305 years if we rounded the nearest year. Okay, last issue. When are we out of here? 2 miles. Oh, okay, well, we're probably not going to get this one. We'll look at this one next time, but this will get you going. Inhibited growth model is the last one, and it's not a big deal.